Thank you for this invitation. When I saw the program, I hadn't thought of that I was going to be coming here. When I saw the program for this session in particular, I thought I should definitely make the trip. And thanks to Jared for making a place for me. The only disadvantage, of course, is that I have to be here now rather than going to one of the other talks, so that all the things so I'm not going to learn anything new today. I'm going to be talking about some old work, which is, and it occurred to me just this morning that maybe not everybody who comes to this kind of conference has reason to be interested in p-adic L functions, much less the square root. So I may not be providing enough motivation. I'll try to add something to the slides. The work was done 5 or 6 years ago, but there's a new insight into the work that's based on the p-adic Fourier theory that Sean mentioned with Graham and van Hoften, and I want to get to that at least. So the starting point are tensor product L functions, otherwise known as Rankin-Selberg L functions, and they're going to be attached to pairs of automorphic representations of unitary groups. Again, why unitary groups? Really, the idea is to look at automorphic representations of GLN, which are the basic universal objects, but the best approach to them and to study them arithmetically is through Shimura varieties, which are attached to unitary groups. So here, some notation. Unitary group, G is a UN, and H is a UN minus 1. And we fix a prime that splits in this imaginary quadratic field. And then lowercase pi and pi prime are the cuspidal automorphic representations of these unitary groups, and the objects for which the L functions are studied are the corresponding representations of GLN over this imaginary quadratic field. So we have capital pi at pi prime. And the idea is to study the p-adic properties of special values, or of a special value of this tensor product. The tensor product L function is again, for those who may not have the motivation attached to this pi, because it comes from a unitary group, there is an n-dimensional Galois representation attached, and the L function, the tensor product L function, which you're going to see momentarily, is the L function of the tensor products of these two n and n minus 1 dimensional Galois representations. So these, in the case of n equals 2, these have been studied extensively, and they are related. For example, the Gros-Zagier formula, which you may have seen, or as generalizations in some of the other sessions, is the first special case of what I'm going to be talking about. So the point of interest today is the central value. This would be, if this were the L function of an elliptic curve, would be at the S equals 1, but because we're looking at automorphic L functions, the center is S equals 1/2. And there is a formula, an explicit formula for the central value, which was conjectured by Ichino and Ikeda and by a WTAG student, Neil Harris, which has been a theorem for some time due to this long list of people. It's a remarkable formula that expresses the value of an L function. Remember, the L function is defined by an integral. It doesn't converge absolutely at S equals 1/2, but it has an analytic continuation. And then this value at S equals 1/2 has a remarkable description, which I will have to describe in several slides. So first, we take this this value. You can ignore the superscript S. This is just a way of saying that we're not paying close attention to ramification. We divide by the L functions of the adjoint representation of the L group of the unitary group, and these all of these L functions, all these values are critical values in the sense of the Dedekind conjecture. So there's nothing terribly mysterious about the transcendental factors. They are defined as explicit periods of integrals of the very kinds of periods that we've seen in the period discussion. And so you take this ratio. The denominator represents, is, if you're familiar with the Taylor-Wiles method, deformation theory. Somehow the deformation theory of Galois representations is built into this normalization. Then there's a formula. So now that the value of the L function, that is this part, this is the part we're trying to study. These are local correction terms. These are some simple factors. And then this is the part that is the period. So it is an explicit, you ignore everything except this. This quantity can be given as an explicit product or ratio of integrals. And there's the ratio in question. Notice, so the denominator, notice that this is homogeneous in f and f prime, so there's no dependence on the choice of f and f prime. F and f prime are explicit automorphic forms in these in the representations we started with, lowercase pi and pi prime. And what we're doing is the denominator is the Petersen inner product, which is needed, and the numerator is the interesting part. You integrate one form multiplied by the other one over the smaller group, the adelic points of the smaller group. That is the and that's a period. That is an explicit period. It is a period in the automorphic sense, which is in principle not necessarily the same thing as a motivic period, but in fact it is a motivic period. All right. And there's something has been, I've ignored an important point. Really, the L function, as I say, is attached to the automorphic representations of GLN, in other words, of the Galois representation over the imaginary quadratic field. But you had to pick out a specific unitary group. So the next few slides say that you have to do something based on the local Galois-Prosod conjectures tell you that this is only interesting if you choose the right specific unitary groups. Otherwise, you get zero. And how can you possibly get zero on both sides? Well, to go back, the periods will vanish. If you pick the wrong unitary groups, then these integrals, these are local integrals, which I won't describe, will also vanish automatically. Okay. It's possible you cannot pick the correct unitary group. That's because there's a parity obstruction, in which case the L function vanishes, and then what you would be interested in is the derivative, but we're not going to be talking about that. All right. So as I said, it's capital Pi and pi prime are supposed to contribute to the cohomology of locally symmetric spaces attached to GLN. And then this is a critical value. And as I said, it's understood by the conjectures of Deligne and Bloch-Bellinson. And because it's the central value, just as the central value of the L function of elliptic curve by the Birch-Swinnerton-Dyer conjecture, when normalized by a period, is a square, essentially a square. The same thing happens in complete generality for the central values. This is somehow a universal property that was observed in the Galois-Prosod conjecture, the Ichino-Ikeda conjecture. So we cannot, in order to, if you want to construct a p-adic L function, usually you let the argument, the S vary, but you can't do that because we're only looking at the central value. So what we have to vary p-adically, analytically, are the pi and the pi prime. And we do that by letting the, in this, what I'm going to talk about, it's only the pi prime that's going to vary. It's the f prime that will vary in the Hida family. But this is just one of many possible directions to take with p-adic interpolation of special values of L functions. And for the square root, this is essentially the beginning of the story. And again, I will not say too much about this, but every choice of specific data, specific unitary groups and specific local factors in the unitary group corresponds to a different branch of a p-adic L function. And this is specific and particularly important for the Archimedean factor, the representations of the unitary groups. What are the signatures and what are the particular representations in the L packet? And I'm only going to be working with, in this talk, with one particular branch, and the reason for that is that this is the only one that has been studied. But as I say, it's a vast field that remains to be developed. All right. In some cases, the period integral can be interpreted as a cup product in coherent cohomology. And these have been classified in my work with Kobayashi and Hsieh, which is on the verge of coming out. In other cases, they cannot be interpreted as cup products. And so it's a total mystery how to define p-adic interpolation. I'm looking at the case where the F is a holomorphic form on the larger group, and the F prime is an anti-holomorphic form. So when you restrict it, this integral does automatically interpret as a cup product. But F prime is in a Hida family, so in fact, you have to apply some differential operators to the form of the bigger group in order to allow it to pair with families of varying weight. This is a well-known phenomenon for people who are familiar with this sort of thing. And there are already interesting unsolved questions in the case n equals 3, and there's a joint, more developed theory with Hsieh and Yamana, which I will not get to talk about. So let me say something about the coherent cohomology. We're going to be working over integral models at P. So we have an embedding of Shimura variety. We fix the signature. So the signature of V is Rs and R minus 1, S, R plus S equals N. We fix level subgroups that are maximal at P. And so we get an embedding of the Shimura variety. And as I said, F is a section of a certain automorphic vector bundle. In other words, a modular form. F prime is a top degree coherent cohomology class. And so, as I said, holomorphic and anti-holomorphic modular forms. Okay, these are pedantic digressions, which nobody wants to see. So in order to develop a p-adic theory, I'm going to be working in the Katz-Hida theory of p-adic modular forms. The special fibers contain open, dense, ordinary loci. And each of these has a pro-étale Igusa cover. In the case of V, the covering group is one of those p-adic Lie groups. So this is the kind of p-adic Lie torsor that Sean was talking about. So it's precise. So the theory does apply and is relevant to this. And we're going to be working on in order to find something in characteristic 0, we work on the rigid analytic Igusa towers, which are also, how do I do this? So, and the p-adic modular forms are, in the first place, functions, just the analytic functions at the top of the tower. All right. So these are p-adically complete OK algebras. And now, very interestingly, I don't remember whether I mentioned this K infinity, or if I did, I didn't say enough about it. This capital K infinity, K prime infinity are the maximal compact subgroups of the respective unitary groups. So K infinity is UR cross US because we're in maximal compact in URS, and UR minus 1 cross US. These are isomorphic as algebraic groups, but over the algebraic closure to the covering groups of the Igusa cover. And this is part of the structure. And so we can choose a maximal Q torus contained in the, this is theory of CM points in the maximal compact subgroup. And we can think of this also as a maximal torus in the p-adic covering group. All right. And so starting with this torus, we look at its ZP points, and we define the rigid analytic weight space whose points valued in CP are just homomorphisms, continuous homomorphisms of this p-adic Lie group, the torus. And this allows us to define inside the ring of all p-adic modular forms the space of forms of a fixed weight alpha, where alpha is a highest weight, is a weight, which could be an algebraic character, or it could just be a p-adic analytic character. More technicalities. For reasons that I don't completely understand, the theory, I understand up to a point, the theory only gives a p-adic L function in the first place of if the number of variables, the rank equal to the minimum of R and S. And so this gives a quotient of the torus, which I call T sim, and the characters of this T sim are spanned by the ones called symmetric in, you don't need to know the definition number of, in this definition from the paper of Eischen, Fintzen, Mantovan, and Varma, which is the basis for the theory of differential operators I'm going to be describing, p-adic differential operators. So there is no theory in the case of definite unitary groups, although there is a theory of p-adic L functions constructed by a completely different method by Hsieh and Yamana in the case of GL3 cross GL2. So here's the p-adic measure. So we start with a p-adic modular form of weight kappa. This is in fact going to be an actual classical modular form realized as a p-adic modular form. Then there is a measure valued in the ring of p-adic modular forms on the torus, the p-adic points of the torus, characterized by the property that the integral of any p-adic character is equal to the image of f under a certain operator, which I construct in the next few slides, which specializes in certain cases to a differential operator. Right. So if chi minus kappa is a positive algebra, so this is theta chi minus kappa. When this is a positive algebraic character of this symmetric torus, then it is closely related. This is a p-adic version of a certain Moss differential operator as applied. So the Moss differential operators are differential operators that take holomorphic modular forms to nearly holomorphic modular forms. And in the p-adic theory, there are these differential operators, and they play the same role in the sense that they're as distributions on forms on the smaller group, they have the same effect as integration against the image of the f under this non-holomorphic differential operator. So in other words, this is an algebraic, p-adic algebraic realization of a non-holomorphic differential operator. All right. You go back one slide. Mm-hmm. So this is just defining the measure which has this property. Yes.
Closely related.
It's closely related. Yes, it's as it so if you apply this, roughly speaking, and up to normalization, you apply this theta to f, and then you integrate, assuming it's a positive algebraic character, you integrate against our f prime. So you could define a distribution on p-adic modular forms on the smaller group, or anti-holomorphic. I mean, this is the Hida family. It has the same effect as integrating on classical anti-holomorphic forms as integrating against the image I could have written, since there's space, I could have written this Moss operator. In other words, there's an identity f prime integrated against, let's call it delta theta minus kappa of f, which is a Moss operator applied to f, is the same thing as f prime paired in the p-adic sense with theta chi minus k kappa of f.
Everything inside is p-adic, right?
No. The delta is a nearly holomorphic differential operator. That's something that comes from the Archimedean theory, classical theory. So maybe if you remember. Oh yeah, okay. So maybe I should have said f started out life as it was a lowercase f. When capital F is a lowercase f, it was a holomorphic modular form. It's being realized as a p-adic modular form, and it's been promoted to a capital F. And then you see, here is where not having an iPad is a disadvantage, because I cannot write what the formula that would make everything perfectly clear. If you apply this delta operator to the lowercase f and you integrate it against this f prime, it's the same thing as applying this theta to the uppercase f, which is the same thing as the lowercase f, except thought of as a p-adic modular form, and pairing it with the p-adic anti-holomorphic form.
I suppose in case to agree, they must evaluate just rational on the algebraic number.
Yeah. And things have to be normalized. Yes. Yeah, they had better read algebraic number. Yes. But the thing is that this gives you a p-adic interpolation of those algebraic numbers. Okay, thank you for forcing me to clarify this. All right. But this theta is defined for any p-adic character, and the values outside the positive range are of particular interest for some other applications. But in any case, you get a p-adic differential operator if lambda is a dominant character. So this is a p-adic differential operator, which is defined by p-adic differential geometry in the sense developed on the Certate moduli space developed by Eischen et al. And this p-adic differential operator is defined in a non-obvious way. We define a p-adic character to be a continuous. We only consider characters to be continuous group homomorphisms that arise as the p-adic limit of dominant characters. So now we're going to restrict our attention to those characters that can be written as the p-adic limit of dominant, but they all can be. We view them only in this way. So, and then we write characters multiplicatively, except when they don't. So here's the story. For any p-adic character, there exists a p-adic differential operator with a property that when you apply it to modular forms of p-adic weight alpha, you get a p-adic modular form of p-adic weight alpha times lambda. Now, there is a different construction in the paper that I mentioned that allows for its evaluation at characters of finite order. And this is the main reason I wanted to talk about this, because I'm so happy to see this. You'll see why. And I'm going to have to build up to it. It's the topic of the second half of the talk. I do not know what time it is. So are there any questions? Okay. I'm perfect. All right, let me say something about the definition of these differential operators in their previous version. So we take the limit in the operator norm, and then we get this theta lambda. But the lambda have to tend to infinity in the Archimedean topology. Otherwise, you do not get the right answer. So if you take the trivial character and you just don't do anything, that's the wrong answer. You have to, the differential operator corresponding to the trivial character is a p-adic differential operator of infinite order. So there's the example. This is how you write it. You can do it in any way. Obviously, it's important that it doesn't depend on the choice of lambda i's. And then you see that for example, I mean, the actual fact is that theta lambda times theta lambda prime composed with theta lambda prime is equal to theta lambda times lambda prime. So in particular, if you theta lambda itself factors through theta 1, the trivial one, and theta 1 is a projector. All right, what is this projector? So every value of the measure factors through this theta 1. So here's a proposition with no content, or you could say this proposition is a definition. It says the theta 1, the image of theta 1 is p-depleted. Now this has a concrete meaning in the classical theory of p-adic modular forms, of modular forms. What it does, you take your classical modular form, an eigenform, and then you replace it by the one that only has the Fourier coefficients an, where n is prime to p. And that is a modular form. You can write it by a simple formula. And what they did not mention, Eischen et al. Did not mention is that this operator is actually does the p-depletion in this particular case. Well, the correct notion is unclear, but I think that when I wrote that, it was unclear, but now it's clear, thanks to work of Sean et al. But basically, you can read it off from the Sertate expansions around any point in the ordinary Gusa tower. The expansions are indexed by coefficients. The index are by S matrices with is EP. And basically, you are doing the same thing I just mentioned in the case of the Fourier coefficients. You remove all of the Fourier coefficients that somehow include P in them. And the reason you want to do that is if you want to take, you don't want to take arbitrary roots of P p-adically. That's not a good procedure. So roughly it preserves, so in the case of, it preserves A alpha of F with F of maximal rank modular P and sets the others to 0. So here I'm going to skip this. So I said the construction, you may want to do one of two things. Maybe I may have wanted to do one of two things. Anyway, I wanted to do the second one, but Sean told me I had to do the first. That's how it's actually first. So this is what happens to the Sertate expansions. But what you get in a very indirect way from this is that that is definitely not obvious from the construction of Eischen et al. Is that this p-depleted form is classical if F is, and that's really important because otherwise you're not sure that your p-adic the p-adic integral I'm going to define actually specializes to Archimedean integrals. And if you take a chi of finite order, then theta chi of F is obtained from your F by applying an explicit element of the group ring of the p-adic points of your group. So in other words, it is something that could be defined over C as well as over p-adically. So it's the p-adic realization of a complex automorphic form. All right. So how does this work? So the ordinary locus carries a universal abelian variety in its p-divisible group. And the standard Igusa variety, the one that's used by Katz and Hida, parameterizes trivializations of the étale and connected parts separately. And so this explains, so you trivialize the étale part, you trivialize the connected part, and then the automorphisms of the trivial étale group and of the trivial connected group, which is a multiplicative type, act on the trivializations, and this gives you the Gusa cover. But you can do better. We take the universal cover in the sense of Schultz and Weinstein, and this is a cover of the whole p-divisible group by the Tate module. So you trivialize the whole thing as indicated. Oops, pushing the wrong button. Yeah, here. And then you get another formal scheme, which was already constructed by Cariani and Scholze. And in as yet unpublished and largely unwritten work, as I said, Graham, von Hoften, and Howe study the canonical action of the automorphisms of this universal cover, of this standard of the trivial p-divisible group, on the ring of functions on the big Egusa tower, which generalizes the case of modular curves that Sean treated previously, which has been written. I think it hasn't been published yet. Anyway, the group is a semi-direct product of the group that was acting on this regular Egusa tower with this homomorphism from the universal cover of the étale group to the universal cover of the formal group, which can be written as an R times S dimensional universal cover the universal cover of a formal p-divisible group of dimension Rs. So it's essentially an extension of n sub v. N sub v is the unipotent radical of the parabolic subgroup whose Levy component is this L sub v. And the subring fixed by the action of this is the Tate twist of this R by S integral matrices with one Tate twist, is the ring of Katz's p-adic modular forms. And so H acts on these Katz's p-adic modular forms because it's a central. So you get an additional action on the p-adic modular forms that one didn't see before, except this includes the p-adic differential operators and the other operators that you're about to see. So now with a few dualities, and when you trivialize, you have to trivialize ZP1, then they turn this into an action. So this is a canonical Banach space action of a ring of continuous functions on the Tate module of the dual formal group to the endomorphisms of the Katz's p-adic modular forms. The dual p-adic p-divisible group is étale, so this is just a ring of continuous functions on some p-adic manifold. Now inside this, there are lots of continuous functions, and some of them are more interesting than others. The ones that are most interesting are the ones I'm going to write. So we think of this as an action of a matrix space. And the action is continuous in the topology of pointwise convergence. It encodes the action of both of the p-adic differential operators, and when restricted to holomorphic modular forms, it actually encodes the action of the group algebra of this disconnected group, the QP points modulo ZP points of the unipotent radical. So this is the adelic action of the unipotent radical of this p-adic points of the unitary group on the automorphic representation. And it fixes, because the unipotent radical is commutative, it fixes the N and V ZP forms. All right, so this is something that, so we get a construction that has this exposed properties. So we choose an isomorphism so that NVZP is identified with the space of R by S matrices with coefficients in ZP. And now we take the upper right I by I submatrix in this R by S matrices, going from 1 to the minimum of RS. And we let MI of A be the determinant of this matrix. And we let K be the sub-manifold of matrices, all of whose MIs, partial, so these are minors, are invertible. And then for any continuous character of the symmetric torus, which is also of dimension minimum RS, we define chi sub K of A to be just a product of these chi sub I's of the minors. And then we extend it by 0 to the whole thing. And here's the theorem. The measure that I described previously, evaluated at the character chi, is none other than the action of this chi sub n on the p-adic modulator form, except I've now used inconsistent technology. Capital F has now been reassigned to the original classical modular form. Right. In particular, for a positive algebraic character, the action of delta of chi sub n is the corresponding p-adic differential operator. But you get a bonus because now you can calculate the action of the characters of finite order. And here it is. This is the statement that if the function is locally constant, or if they, then, so if you have if you want to translate by a specific element in the p-adic points of the group, you can get that. Yeah, but let me write it this way. So the action of the function corresponding to an element of NV of QP is the same thing as the action in this p-adic Fourier theory is the same as the action, just the right translation by that same element. So every element in the unipotent radical defines a continuous or locally constant function on the Tate module of the dual, and these actions coincide. So in particular, as I have been saying, and I don't know what this M is, I'm sorry, the image of a locally constant function is a classical modular form. All right. So we can apply this to the case where phi is chi sub n for a character of finite order. And then we get the integral of this character, which is the value of this measure on a character of finite order. And here's the formula. Now, so it doesn't look all that promising. However, in the case where n equals 3, and it doesn't depend on the order. I mean, if it's of order m, then for any m prime bigger than m, you get an explicit formula for it. And but when S is 2, 1, this is up to some various normalizations. This is precisely the expression that Yamana discovered to evaluate the p-adic measure at this character. He found it I suppose by trial and error. And what's remarkable is that this. So let me just back up again for people who are not so familiar with the mechanics of p-adic L functions. A p-adic L function interpolates not the precise values of the classical L function. First, you have to divide by the transcendental part, which is already built in, but you also have to change your Euler factors at infinity and at p. The formula for this was originally written down by Coates and generalized by Coates and Perrin-Riou. And usually in these constructions, the hardest part is to figure out what to do with how you recover from the Archimedean theory, from the classical theory, the automorphic theory, the predicted Euler factor at p, modified Euler factor at p. So in the very, very first case of this sort of thing in automorphic forms, which was the Mazur-Swinnerton-Dyer p-adic L function, it just comes out. They do it by classical means, but if you try to do this in higher dimensions, it gets really complicated. You really want to separate this into the purely local construction. And the good news is that with this formula, in the case of U21, Yamana was able to calculate the Euler factor that you have with this particular choice. And again, in the general automorphic theory, the automorphic theory, you get test vectors in each local place. If you remember the Ichino-Ikeda formula, there was a local integral at all of the ramified places. And you can get the same answer infinitely many ways by picking some test vector. And why would you pick one rather than the other? Well, this theory picks out one which happens to be precisely the one that Yamana hit upon. All right. There's more to it. So let's suppose that pi p is a principal series for your original automorphic representation. Some induced character would be the Borel. So as a representation of this maximal parabolic, it has a filtration with the subspace pi p0 corresponding to the space of functions. So an induced representation, a principal series representation, is induced from the Borel. We look at the Brouwer decomposition or the partial Brouwer decomposition functions that translate on the left under B by the character alpha, and then you write G of QP as the union of over certain elements of the Weil group of B times W times P sub V. And there's one space of functions which is a subspace, with, namely the ones that are supported on the big cell. And the corollary is that the measure takes values in the closure of this space of classical modular forms, in the space of p-adic modular forms. So in particular, the image of the differential operator are actually contained in a particular closure, Banach space closure, in the space of p-adic modular forms. So questions. Several questions arise. What can be said about the representation of the ZP points of the parabolic on this Banach space? Is it purely local, or does it depend on the automorphic representation? Apparently, Sean has done some work, at least in the GL2 case, that suggests that it's purely local. It doesn't depend on anything except the original pi. So in the next part of the talk, which will, I guess, be the last part of the talk, this measure is now integrated against or contracted with a Hida family on the smaller group to define a square root p-adic L function. So, okay. So I will skip this. We take on the, so what is the Hida family? Well, the Hida family technically is based on ordinary holomorphic representations of the smaller group, in this case, the smaller group, but any such thing gives by a process of conjugation an anti-ordinary, anti-holomorphic representation, and that's where our form F prime is going to live. So we take Hida's Hecke algebra acting on ordinary holomorphic forms, and then we localize, we complete at an irreducible component corresponding to a residual Galois representation attached to this tau. I remind you that there was an n-1 dimensional Galois representation. We reduce it mod p, and we complete the Hecke algebra at the corresponding. All right, so the Hida family consists of all ordinary holomorphic forms except in this anti-holomorphic realization, with the property that the corresponding Galois representations are congruent to the one of interest. And this maps to the weight space for the Iwasawa algebra, and Hida theory tells you that this is a finite flat map to the Iwasawa algebra of the maximal torus in this subgroup. And which means in particular only finitely many forms over any given weight kappa prime, but there are infinitely many possible weights. So all the weights that are kappa prime that are congruent to our original weight, whatever, which I think was also called kappa prime, but so all of the weights in a family. And the contraction is precisely the p-adic interpolation, so of the periods that I wrote, where this delta somehow disappeared from the slide. That would have answered Jared's question if I had not somehow erased that slide. So to go back, what we do is we apply a non-holomorphic differential operator to our F, which is now a capital F, and then we integrate it against an F prime indexed by X, which is a point in the Hida family. And if it's a classical point, then we get an actual integral. But if it's not, we can still do a p-adic pairing, and that gives you the p-adic interpolation of the periods. Okay. Now, if we do this under nice hypotheses, if the Hecke algebra satisfies an appropriate, it's not terribly singular. In practice, one can prove that it is very often a local complete intersection by the Taylor-Wiles method. And this is what I proved in a paper with Atanasov. And the image is not too small, then it can be, anyway, what we get in the end is an element of this completed Hecke algebra. So this is the final formula. We must be getting close to the end of the time, 5 o'clock. Yes, very good. This is where I wanted to arrive, amazingly. So here is the formula. So this is the period that you first saw in a more general form in the Ichino-Ikeda Neil Harris formula. This is one of the periods, product of two of which give you, or the absolute square, the absolute value of which gives you the special value of the classical L function at the center. And this tells you that there is an element in this Hecke algebra which specializes at the point X, because X is a point in the spectrum of the Hecke algebra, the classical form, is exactly this normalized period. All right. So this has only been worked out for imaginary quadratic fields, but it can be proved for general CM fields, but at the cost of much more notation. And it's only written for kappa prime varying in a one-dimensional subfamily, because this is what was most easily extracted from the construction in Eischen et al. But I believe that now with this new construction of the p-adic differential operators, it can be extended to a maximal family. And so this, in other words, if you take this, and for every classical point, it's an algebraic number, which this is just reiterating the Ichino-Ikeda formula. What happened to the Petersen norms? Well, that was what you needed in order to replace. When you divide by the Petersen norms, it turns out that what you get is an algebraic number. So that's why this works. When you divide by the, yeah, right. This is actually, yes, when you, no, sorry, it's the other way around. When you multiply this, remember there was an adjoint L function in the denominator. When you multiply by the square of the Petersen norms, then you get an algebraic number. And then this Z sub S incorporates all of the stuff that we didn't calculate, except that now there's a calculation, at least when n equals 3, of the Archimedean and p-adic, in fact, of all of the factors, because Yamana is nothing stops Yamana when he wants to start calculating. So I guess, yeah, that's, so all I want to say is that to reiterate, well, I'm not going to have time to talk about. There should be a theory whenever, for every branch, that is to say, for every possible configuration of discrete series of modular form for the bigger group and some other discrete series for the smaller group that is contained in the restriction. And when the restriction map corresponds to a cup product or restriction on coherent cohomology, then there is some hope in generalizing this, but this would require developing all of this theory of differential operators for higher Hida theory, and that's a project for the future. Okay. So.
Is my mic on? Anytime I have one, you scroll back to what was like main formula involving a square. times the value of an L function.
Yes.
So if I put the same flavor as last time, it's fusion between p-adic and complex numbers.
Right.
That's what? It seems like the L of f tau x is I mean, a priori, living in a QP or CP bar.
Yeah. But but it says that if x is a classical point, then it is actually an algebraic number.
One of the Archimedean.
So we take yeah, so there is it's an algebraic number in some field of definition of automorphic representation, and you take, and so let me back up on motivic L functions. When you have the conjecture of Deligne for motivic L functions, works with motives with coefficients in a number field. And so for each complex embedding of this number field, you get a different L function. And in this case, the coefficients come from the rationality of the automorphic representation. And so what I did not mention, is that you had to embed this number field, coefficient field, in the complex numbers. However, because we were working with complex automorphic representations, the coefficients are already embedded. So an example of the coefficients are the field of generated by the Fourier coefficients of a modular form, of a Hecke eigenform. So in general, these coefficient fields are specializations of the Hecke algebra. These are the Hecke algebra is, the big Hecke algebra is something that specializes to the Hecke algebra generated by the values of the Hecke operators. So it's a p-adic algebra that has these specializations.